Number 70 in chapter 19 asks us to calculate the energy produced per mole of uranium-235 for the neutron-induced fission of U-235 to produce tellurium-137 and zirconium-97. And so if we look at what's happening here, we really have uranium-235 plus a neutron then is turning into tellurium-137 and zirconium-97. And so we're trying to figure out the energy produced upon this reaction, and that is really a change in mass or a binding energy. And so we really want to use this equation, E equals mc squared, or the change in energy is really a resultant in the change in mass that we actually observe in the fission reaction. And so we need to first figure out our delta M, and that delta M is simply going to be the sum of our masses of our products minus the sum of our masses for our starting materials. And so what we need to do is figure out, okay, well, what are our starting materials, what are our products, and then we have to use their masses, which are actually given in the table. So to begin, we have to make sure that we balance our reaction. And so one thing that we have to realize is that from the language, we are told that we are making tellurium-137 and zirconium-97, but this nuclear reaction is not balanced. And so in order to balance it, we have to add 2 neutrons to make sure that our reaction is balanced with neutrons and with protons. Now that we have our balanced reaction, we can determine the delta M, because they tell us our masses for our product. So for tellurium-137, that atomic mass is given to us as 136.9253, right? And so what we're looking at here, these are really just atomic masses, but we're looking at how this change in atomic mass then results in energy, right? And that's the idea of fission, that once we then take uranium-235 and then it undergoes fission to produce tellurium and zirconium, there is a change in the mass. And as a result of that change in that mass, there is then energy produced. And so we need to add up those masses given to us. The tellurium is the 136. The zirconium is 96.91095. And then we made 2 neutrons, so we would take 2 times our mass for a neutron, which is 1.008, 66492. And so those are our products. And so now we're subtracting off from that our starting materials. And so our starting materials will be the uranium-235, which is given to us as 235.04392. 22 there, plus then our neutron, which is 1.008, 66492. And so we solve for that, we get our delta M, I'm just going to put this at the bottom here, as a negative 0.19900708. And that is in AMUs, or, remember an AMU is really just a gram per mole. So that's the change in the atomic mass units, right? The change in our protons and neutrons that is occurring. And so now we're going to plug that value up into our delta E equals delta MC squared. And we see that because of that negative value, our change in energy is going to be negative, and so that's energy produced or released, right? And so we're going to now take our expression for delta E, and we're going to plug in our delta M. Now, one thing we have to be very careful of is that we have to realize that this cannot be in this cannot be in grams per mole. This has to be in kilograms per mole, because remember, what is a joule? It's a kilogram meter squared per second squared. Right? And so that's why we have to make sure that that delta M is not in grams per mole, but in kilograms per mole. And then C, remember, is the speed of light. Well, 3 times 10 to the 8th meters per second, that quantity squared. So kilogram meter squared per second squared is a joule. And so this gives us a value of joules per mole. And so when we plug that in, we get a value of negative 1.791 times 10 to the 13th joules per mole, or 1.791 times 10 to the 13th joules per mole of uranium-235 was produced. That is number 70 in chapter 19, which is looking at how a change in atomic mass for a nuclear fission reaction, how and why that produces lots and lots of energy. As we can see here with our 1.8 times 10 to the 13th joules per mole, or 10 to the 10th kilojoules per mole. Either way you look at it, that is a very large value.